Right now, at this exact moment, the fastest object humanity has ever launched into space is traveling at 61,000 kilometers per hour. That is the Parker Solar Probe, the pinnacle of human engineering, the fastest thing we have ever built. At that speed, it would take 7,230 years to reach our nearest neighboring star. Not 7,230 days, not 7,230 months, years. Every civilization that has ever existed on Earth, combined, has not lasted 7,230 years. And that is the closest star. The one right next door, our nearest neighbor in a galaxy of 400 billion stars. Today, I'm going to show you exactly why the distance is only the beginning of the problem. Why, even if we solved speed, 5 other barriers would still be waiting. And why the universe may have been designed in the most cruel way possible to keep civilizations permanently imprisoned inside their own solar systems. Our target has a name, Proxima Centauri. It is a small red dwarf star sitting 4.24 light-years from Earth. Part of the Alpha Centauri system, a family of 3 stars orbiting each other in the constellation Centaurus. Proxima is the closest of the 3, and orbiting it, scientists confirmed in 2016, is at least 1 planet, possibly 2 or 3. The confirmed planet, Proxima b, sits in the habitable zone, the region around a star where temperatures could theoretically allow liquid water on a surface. Rocky, roughly Earth-sized, in the habitable zone. On paper, it is the most exciting planet ever discovered, the closest potentially habitable world we know of, and we cannot reach it. Not with current technology, not with technology being developed right now, not with any technology whose underlying physics has been proven to work. And the reason starts with a number that the human brain is genuinely not built to process. 4.24 light-years. That is how far away Proxima Centauri is. A light-year is the distance light travels in 1 year. Light moves at 300,000 kilometers per second. In 1 year, it covers about 9.46 trillion kilometers. Multiply that by 4.24. Proxima Centauri is approximately 40 trillion kilometers from Earth. Let's make that feel real. The distance from Earth to the Moon, 384,000 kilometers. You could drive that in about 5 months at highway speed. The distance from Earth to the Sun, 150 million kilometers, about 170 years of driving. The distance from Earth to Proxima Centauri, 40 trillion kilometers. Driving non-stop, it would take over 40 billion years, 3 times the current age of the universe. And our fastest probe, Voyager 1, has been traveling for 47 years. It is currently about 24 billion kilometers from Earth. Which sounds impressive, until you realize that Proxima Centauri is 1,700 times further away than Voyager 1 has traveled in 47 years. At Voyager's speed, it would take 73,000 years to arrive. At Parker Solar Probe speed, the fastest we've ever achieved, 7,230 years. These numbers are not engineering problems, they are physics problems, and the physics gets worse, not better. the faster you try to go. The obvious solution seems simple: build a faster ship. If 61,000 kilometers per hour takes 7,230 years, go 1,000 times faster. Get there in 7 years. The problem is Einstein. According to special relativity, as an object with mass accelerates toward the speed of light, its effective mass increases. The faster you go, the heavier you become. The heavier you become, the more energy you need to accelerate further. And as you approach the speed of light, your mass approaches infinity. Which means the energy required approaches infinity. An infinite amount of energy does not exist. Therefore, nothing with mass can reach the speed of light. This is not a theory. It is one of the most tested and confirmed principles in all of physics. But even if you could somehow reach, say, 10% of the speed of light, an extraordinary speed requiring energy we cannot currently generate, the journey to Proxima Centauri would still take 42 years. At 20% the speed of light, which breakthrough Starshot proposes for tiny gram-scale laser-propelled probes, the trip takes about 21 years. And those probes would be the size of a postage stamp, not a crewed spacecraft. For a crewed ship carrying humans with food, water, air, radiation shielding, propulsion fuel, landing equipment, the mass requirements are so enormous that accelerating it to even 10% of light speed would require energy equivalent to thousands of nuclear weapons detonated continuously for decades. The speed barrier is real, and it leads directly to the second problem, one that is perhaps even more fundamental. NASA once ran a quick calculation. They asked, what if we sent a ship to Proxima Centauri using conventional chemical rockets? Arriving in just 900 years without even slowing down. How much fuel would it need? The answer: more matter than exists in the observable universe. That is not an exaggeration. That is the actual mathematical result of applying the rocket equation to interstellar distances. Chemical rockets work by burning fuel to create thrust. The problem is, you have to carry the fuel with you, and to carry more fuel, you need more thrust. And more thrust requires more fuel, which requires more thrust, which requires more fuel. The mass ratio compounds exponentially, and across interstellar distances, the exponent becomes so large that the fuel requirement exceeds the mass of everything that has ever existed. This is called the Tsiolkovsky rocket equation problem, and it eliminates chemical propulsion entirely for any mission beyond our solar system. Alternative propulsion concepts exist: nuclear pulse propulsion, antimatter engines, laser sails. But nuclear pulse propulsion gets you to maybe 10,000 kilometers per hour faster. Antimatter, the most energy-dense fuel theoretically possible, humanity has produced less than 20 nanograms total, ever, in all of human history. A single gram of antimatter would cost approximately $1 quadrillion to produce, and you'd need tons of it. The fuel problem has no current solution, and the third barrier is one that no amount of engineering can build a wall around. Between stars, there is no atmosphere, no magnetic field, no protection of any kind. What there is constant radiation, cosmic rays, high-energy particles fired from dying stars, and supernova explosions across the galaxy, stream continuously through interstellar space. On Earth, our magnetic field deflects them, our atmosphere absorbs them. We receive an annual dose so small it's almost irrelevant. In interstellar space, For a journey of 20 or 40 years, a crew would be exposed to the full, unshielded force of cosmic ray radiation for every single day of the journey. The cumulative dose over 20 years in deep space would be catastrophically above any safe limit. DNA damage, increased cancer rates, neurological deterioration, cataracts, immune system failure. And here is the cruel physics. The faster you travel, the worse the radiation gets. Because at relativistic speeds, even the thin hydrogen atoms scattered through interstellar space become radiation. At 10% the speed of light, hydrogen atoms hit your spacecraft like a fire hose of gamma rays. Shielding helps, but shielding has mass, and mass, as we just established, is the enemy of speed across interstellar distances. Every kilogram of shielding requires more fuel. More fuel requires more mass. More mass requires more fuel. The radiation problem and the fuel problem are locked in a vicious cycle, each one making the other worse. Let's say, somehow, we solve propulsion, we solve radiation shielding, we achieve 10% of the speed of light. The journey still takes 42 years. The crew that leaves Earth arrives at Proxima Centauri 42 years later. If they were 30 years old at launch, they are 72 on arrival. If the journey back is another 42 years, they would be 114 years old on return. They would not survive the round trip. So you send younger people, but then the people who land on Proxima B's surface were born in space. They have never seen Earth, never felt real gravity for their entire childhood, never breathed unfiltered air. And the people who sent them, the scientists, the engineers, the families who said goodbye, will all be dead before the first message arrives back. Because the communication delay alone at 4.24 light years distance is 4.24 years one way. A conversation takes over 8 years round trip. We've arrived safely, sent from Proxima B, arrives on Earth 4 years later. Congratulations. Sent back, arrives another 4 years after that. The crew is completely isolated. Decisions they make, Earth cannot respond to in real time. Emergencies they face, Earth cannot help with. They are alone, permanently, irreversibly, in a way that no human being in history has ever experienced. And even if they survive all of that, even if they land, what they find at Proxima B may be the cruelest discovery of all. Proxima B orbits in the habitable zone. That is true, but habitable zone only means the right distance from the star for liquid water to theoretically exist. It says nothing about what the star itself is doing to the planet, and Proxima Centauri, the star, is violent. Red dwarf stars like Proxima are known for producing extreme stellar flares, sudden, massive bursts of radiation and high-energy particles that blast everything in close orbit. Proxima B orbits its star once every 11 days. It is extremely close, meaning those flares hit it directly, repeatedly, constantly. Scientists studying Proxima's flare activity have concluded that the radiation environment at Proxima B's surface is likely hundreds of times more intense than Earth receives. Any atmosphere Proxima B might have could be slowly stripped away by those flares, just like Mars lost its atmosphere to the solar wind. And Proxima B is almost certainly tidally locked, one side permanently facing the star, baking in heat, the other side in permanent darkness and cold. The planet we spent 42 years traveling to, the one we risked everything for, may be a radiation-blasted, airless, tidally locked rock. Completely uninhabitable, with no way to know for certain until we're standing on it. And the last barrier is the one that might make all of this permanently impossible. Not for engineering reasons, not for physics reasons, for time reasons. Here is a question nobody asks out loud. How long does a civilization last? Human civilization, in its current recognizable form, is roughly 10,000 years old. Writing, cities, agriculture, organized society, all of it, 10,000 years. The technologies required for interstellar travel, if they are even possible, likely require centuries of development beyond where we are now. Some estimates suggest a minimum of 200 to 500 years before the engineering could conceivably exist. That assumes continuous technological progress, continuous global cooperation, continuous funding. No wars, no collapses, no pandemics bad enough to set us back, no climate catastrophe disrupting the industrial base that produces the science. History does not suggest that civilizations progress continuously for 500 years without major disruption. The Bronze Age collapse reset Mediterranean civilization by centuries. The fall of Rome sent Europe backward for nearly 1,000 years. And we are currently, in 2025, facing simultaneous existential risks that the doomsday clock places at 89 seconds to midnight. The window for building an interstellar civilization may require more stability, sustained over more centuries, than human civilization has ever demonstrated it can maintain. We are trying to reach a star 4.24 light-years away, while not yet certain our civilization will survive the next 200 years in a form capable of attempting it. So, is it truly impossible? Or is there one path, however narrow, that physics actually allows? In 2016, physicist Stephen Hawking and billionaire Yuri Milner announced breakthrough Starshot, a project to send probes to Proxima Centauri within a human lifetime. The approach: strip everything away. No crew, no life support, no fuel tanks, a probe the size of a postage stamp, a star chip carrying a camera, a transmitter, and almost nothing else. Total mass, a few grams. Accelerated by a 100 gigawatt laser array on Earth. A laser so powerful it would consume the energy output of a small city for the few minutes of acceleration. The star chip would reach 20% of the speed of light and arrive at Proxima Centauri in approximately 20 years. It would sweep past Proxima b, far too fast to stop or orbit, taking photographs and measurements in the few minutes of closest approach. Then transmit that data back to Earth over the following 4 years. Total mission time from launch to first data back, roughly 24 years, a human lifetime, actually achievable, in theory. But in October 2025, Scientific American reported that breakthrough Starshot has been quietly struggling. Technical problems with the laser sail materials, engineering challenges nobody has solved, funding questions. Even this, the most ambitious, stripped-down, physics-allowed approach to reaching our nearest star, is fighting for survival. And even if it works, it sends a gram of electronics past a planet at 20% light speed. It does not send a human. It does not establish contact. It does not build a future. It takes a photograph, from a postage stamp, falling past at 60,000 kilometers per second with no way to stop. 4.24 light-years, our closest stellar neighbor, the easiest possible destination beyond our solar system. And the barriers between us and it are not barriers of ambition or funding or political will, they are barriers written into the laws of physics itself. The speed of light cannot be reached, the fuel required cannot exist, the radiation cannot be fully blocked, the journey outlasts human lifespans. The destination may be uninhabitable, and the civilization attempting it may not survive long enough to finish. The universe is not empty. It contains hundreds of billions of galaxies, each containing hundreds of billions of stars, each potentially surrounded by planets, and almost all of it is permanently, physically, mathematically beyond our reach. We are not imprisoned by walls, we are imprisoned by the speed of light, by the curvature of space-time, by the rocket equation, by biology, by time, by the universe itself. And here is the thought that should keep you awake tonight. If these barriers are the same for every civilization in every solar system across the universe, if every species that has ever evolved faces the same physical prison we do, it might explain something that has puzzled scientists for 70 years. Why, in a universe of hundreds of billions of potentially habitable worlds, have we never heard a single signal, never detected a single transmission, never found a single piece of evidence that anyone else is out there? Maybe they are out there, maybe they are everywhere, and maybe the speed of light is the reason we will never know. That silence, and what it might mean, is next.